So we've talked about sharing electrons. Just like sharing between people, sharing between atoms is not always equal. So if a covalent bond happens between unlike atoms, it can result in unequal sharing of the electron. Or in other words, one atom pulls the electron in the bond closer to its side. That type of bond is called a polar covalent bond. And when you have a polar covalent bond, you're going to end up, so we have A and B with a polar covalent bond. If B pulls the electrons that way, it's going to end up with a partial negative charge on it. That's a Greek letter delta. And the side with the fewer electrons is going to end up with a partial positive side to it. So our molecule is not equal, but it's not all the way to an ionic bond either. Our example here is hydrofluoric acid. One way to measure bond polarity is using the electronegativity scale. So EN stands for electronegativity. Here's a picture of what it looks like. You can see the red here means negatively charged, the blue means positively charged. And one way to test for polarity is by putting the molecules in an electric field and turning on the current. And you can see that the molecules will align with an electric field, showing the polarity there. Now, most bonds are going to have some amount of sharing and some ion formation. So we need some sort of definition here. So if a bond is covalent, it's not going to have the full electron transfer, but if there's enough unequal sharing to produce a dipole, which means it aligns an electric field, the bond is classified as a polar covalent bond. The way we measure this is with the electronegativity scale. So here's a picture of the electronegativity scale, and one way to check for a covalent versus, polar covalent versus nonpolar is by checking the difference in electronegativity. If you look over here, you see these elements in purple. Those are the elements you have to watch out for. So if fluorine, oxygen, or nitrogen, or chlorine, or sometimes bromine is involved, so halogens, oxygen, nitrogen, you'll want to check and see there could easily be a polar covalent bond there, especially if carbon or hydrogen is involved in being bonded to one of those. Here is your electronegativity difference scale. So if the difference between bonded atoms is 0, it's pure covalent, so there's equal sharing. So that's, things like oxygen to oxygen, they're equal to each other, so that's a pure covalent bond. If the difference is between 0.1 and 0.4, it's nonpolar covalent. If it's 0.5 to 1.9, it's polar covalent. And if the difference in electronegativity is larger than or equal to 2, then the bond is defined as ionic. So if you start getting metal to nonmetal, you're going to end up with an electronegativity difference that gets you an ionic bond. Here's a picture of what I just talked about with the example of chlorine. So chlorine has an electronegativity of 3. Chlorine bonded to itself is a pure covalent. Chlorine bonded to hydrogen, so hydrochloric acid, has a difference of 0.9. Like I said, keep an eye out for the halogens and oxygen and nitrogen for looking for polar covalent bonds. And then here's an ionic example looking at the electronegativity. Your difference between sodium and chlorine is 2.1, so that's an ionic bond. Okay, dipole moments is another way of measuring polarity. You can see here that the difference in electronegativity, so chlorine Cl2 by itself doesn't have a dipole. ClF, there's not that much of a difference. It's only 1, so that's categorized as a non-polar covalent bond. But if you do HF, then you do get the larger difference in negativity, electronegativity, and more of a dipole moment. And then all the way to ionic, you get a very large dipole moment. The thing that really gets affected by these polar bonds is intermolecular forces. And so when you have polarity, you have these slight positive and negative charges interacting with each other, and those polar molecules are going to be more attracted to each other than something like C5H12, which is completely nonpolar and tends to be, they don't stick together as well.